Hi, in this video, we're going to start chapter 18. The first thing in chapter 18 is called the common ion effect. And we already know this because we know Le Chatelier's principle. Basically, if we have an equilibrium system and we add a common ion, so we add an ion that is already in the system. So for example, in this dissociation of acetic acid, we have acetate ions here. We start with 0 of them normally, right? We just put in the acetic acid and then we have the dissociation occur. But if we were to put in some sodium acetate, then we would see that we added acetate ion. When we add acetate ion, we can predict that it would shift to the left. If it shifts to the left, what do you think is going to happen to the hydrogen ion concentration or the pH? Or what's going to happen to the amount of H plus. And so this can change the equilibrium system. That shift is going to affect things. So what I want you to do is I want you to try it. I know you may not be exactly prepared, but at least set up maybe the equilibrium system, set up an ice table, kind of figure out what way you want to look for. Yes, we know it's going to be, we know that it just theoretically we shift this way, but we can't actually shift to the left if we don't have any hydrogen ions. So you'll see how we can handle it with the pH, but just do what you can and follow the rules of ice tables that you already know and try to work this out. The Ka for acetic acid is 1.8 times 10 to the negative 5. All right, so hopefully you were able to work it out. The next couple slides actually take us through it, but I'm gonna work it out for you here. So we have acetic acid. I'm gonna ignore the water because it's not doing anything. And then we have acetate ion. And that's how I draw acetic acid. You could use the choo-choo if you want to, but I use the C2H3OH because it's a little bit easier to see which H is going to be the acidic one or the H is going to come off. And then we have our ICE. Now we have a 0 amount of hydronium. We have 0.10 molar acetic acid. And then it says that we have 0.050 moles in 1 liter. So that would be 0.050 molarity as well. Now, when we're talking about change, yes, we know that if we add something, it will want to push the equilibrium to the left, but pushing it to the left doesn't mean it's going to the left. Like Q is still 0 because we don't have any hydronium. So we still need to think about change as moving toward a 0. Change will always, no matter what we're predicting, move toward the 0. But overall, you might see that it used to be that there were more products at equilibrium, and maybe you're shifting it left means there's a little bit less products at equilibrium. Don't worry about what the Le Chatelier's principle says when we're doing the ice table. Just look at, you cannot subtract from 0. So we know we have to be moving to the right because Q is 0, because products over reactants, 0 on the top is going to make it a 0. And then our E. And notice now we have not just 2 x's over here. We've got 0.05 plus x. So that'll make this a little bit more interesting. Then we have our Ka, which is going to be hydrogen or hydronium. Again, I'm just using hydrogen to go a little faster. As long as you know the hydrogen and hydronium are the same thing when in water. And then we can plug in. You got the hydrogen, and then we have 0.05 minus plus x. And then we have 10 minus x. And then we can set it equal to 1.8 times 10 to the negative 5. And so if we're trying to solve for x, because remember pH is the negative log of H or hydronium, so we need the x here. So we can assume that x is small because K is really small. And if for some reason we can't, we'll check it at the end and just see, hey, it was x really small. When you're checking the x is small, you need to make sure that it is within 5% of the smaller initial. So let's just assume x is small here. When you're doing x is small, you need to actually cross out the x's you want to cross out in your work. So what I'll get is 0.050x over 0.10 is equal to 1.8 times 10 to the negative 5. And I bet you can figure it out from there. And so I'll just kind of scroll down to show you a little bit of that work. So your x should wind up being 3.6 times 10 to the negative 5. And so your pH should be 4.44. Now notice that the pH before we added, we just have 0.1, before we added any extra was 2.87. The concentration of H plus was 1.3 times 10 to the negative 3. Now the concentration of H plus is 3.6 times 10 to the negative 5. It's smaller, right? Because the reaction is kind of leaning more to the left because we added that common ion. So our pH is higher, it's less acidic. There's less H plus in there. So that is reflecting what we understand of if we add a common ion, it's not in the ice table, it's shifting left because we can't subtract from 0. It's an overall, we're going to have less hydrogen ion because it will push the equilibrium a little bit to the left, if that makes sense. All right. Buffers. Buffers are a solution that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. Basically, a weak something and its conjugate partner. Buffers have a job, resist change in pH. So we need to know both what buffers are, what are they made of, and what they do. So when you have a weak acid like acetic acid and then you have a conjugate base, if you put both of them in your solution, now we have a buffer. Usually it's about equal molar, but you can put in different amounts depending on what you need. What does the acid do? The weak acid is responsible for, if you add a little bit of base, it will react with that base to neutralize it. So it totally use up. If I put in so if I have like 0.1 molar here and I put in 0.01 molar hydroxide, this hydroxide will get gone because this acid will just eat it all up. And then what will it make when it takes your acid plus your hydroxide? You make the conjugate base again and some water. So essentially what we're seeing is, and then if you have any acid, so you add a bunch of H plus, which is acid. So remember, base stuff is hydroxide. That's your base stuff. And then hydrogen ion is your acid stuff. And remember that hydrogen ion is the same as hydroxide ion when we're talking about in water. So if I add acid, the base is going to react with the acid. Now this is kind of weird. I know they're showing you this reverse, but it's going to add acid. It's going to make weak acid. So really we're just like shifting the reaction left and right. So that's why in order to be a buffer, it's got to be a weak acid or base. It can't be strong because we need to be able to go left and right to shift the reaction to eat up all that excess acid or base. So what do we do with this with respect to ice tables? So let's say we start with equal molar of our acid and our base. And so we establish a pH. We would do this whole thing, this regular ice table stuff. We establish a pH, 4.74. Let's say we add H plus. So we add 0.1 mole of H plus. Now, when we first started, we have 0.1 mole of H plus. Well, the base is going to neutralize that 0.1 mole. If the base neutralizes that 0.1 mole, we're going to be taking 0.1, it's a 1-to-1 mole ratio, do you see? We'll be taking 0.1 mole from the base and 0.1 mole from the acid to make 0.1 mole of the product. So this will subtract, so we would say like subtracts 0.1. This would be subtracts 0.1. So this would be, say, subtracts 0.1, subtracts 0.1, add 0.1, because we'd be shifting to the right. It's going to be neutralizing. So what do we get? 1 minus 0.1 is 0.9. 0.1 minus 0.1 is, you see, it cancels it out. It totally neutralizes it, and we 1.1. So then we take our equilibrium system that we had, we plug in these new numbers and figure out what our pH is now. You see that our pH now is 4.66. So the original had a pH of 4.74. We had a little bit of acid, so it went down a little bit, but not that much. It would have gone down way more if we didn't have the buffer system there. This is just a way for us to visualize and to calculate how much is the pH going to change if you mess with a buffer. Well, so this part right here, you're always going to have to do this. You always have to figure out how much do you have once you neutralize the, offending acid or base. But do we always want to have to do this ice table for buffers? No, I'm going to give you a present. The present is called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation basically says, I don't have to do an ice table. So I like to write it like this: pH equals pKa plus log of A minus, that's your conjugate base, over HA, that's your weak acid. Basically base over acid, so B over A. What's pKa, y'all? pKa is, what's P? Negative log? What's Ka? Ka. Negative log Ka. So if I give you the Ka, you're doing your ice table and stuff. Now, these are both, these can be initial amounts. I guess, or after, so I guess after any sort of neutralization, if applicable. So, for example, if we want to know what's the new pH, we wouldn't plug in these numbers, because if we're saying, hey, wait, we added acid, so what's the pH now? We plug in these numbers. So after whatever neutralization has occurred, and we just plug those numbers in. We don't do an ice table, which is great. Why don't you try it? Again, the Ka of acetic acid is this. And you try what happens if I add hydroxide. So you've got everything you need. Pause it and try to work it out. Okay, so who is going to react with the added hydroxide? So hydroxide is a base. That's base stuff. Who's going to react with the base? The acid. What's the acid? Acetic acid. Acetic acid is going to react with hydroxide. What's it going to make? Let the acid do its job. It's going to make acetate ion and water. Well, if I put in, if I have 1.00 molar of this, and I started with 1.00 molar of this, I added in, so think about this as like your initial, you could do kind of like a baby ice table for this. It's not exactly the same, but I added in 1.00. So right at that addition, okay, and then we have the change. So what's going to happen? We're going to subtract that 0.1. I'm going to get rid of it. I'm going to neutralize that. That's not going to hang out. And I'm going to add it to this side, because the reaction is going to have to go to the right to neutralize it. The reaction only goes one way for these, actually. No, thank you. No, do not want that. Thank you. So what do I get now? So we have an after, so like an addition and then a change and an after 1.10, 0.90. These are the numbers we're going to use, plug into our Henderson-Hasselbalch. So pH. Let's find our pKa real quick. pKa equals negative log of 1.8 times 10 to the negative 5. So our pKa, I'm going to cheat because I don't have a calculator on me. 4.74, I should know that. So 4.74 plus the log of, we're going to, our base on top over our acid. And then we'll get a pH. Should get 4.83. If you didn't get that, check your work. They have the strategy here to kind of show the work. I did it a little bit different. I do addition, change, and after. It's like ACA. And then does that make sense? We added a little bit of base and the pH went up a little bit, which makes sense, but not up a whole lot because the buffer's still buffering. If you want to make a buffer with a specific pH, Buffers have to have a conjugate acid to base concentrations within a factor of 10. So you can't have like 10 to the negative 3 amount of your conjugate of your acid and then 10 to the 3 amount of your base, right? That's two different. They got to be pretty close to each other. To basically concentration of acid and base need to be somewhat close for the buffer to be effective. Because you need to have both the acid and the base ready to neutralize any oncoming acid or base, right? We need that weak acid and that conjugate base. Both of them there. And a pH of a buffer cannot be more than 1 pH unit different than the pKa of the weak acid. Once you go past that, the buffer can't handle it. So a good buffer, so if we're looking for like what kind of buffer do I want if I want this pH, then you pick a Ka that would match your pH. So pick weak acid with Ka or pKa close to the pH desired. So whatever you're like, hey, I want a solution that'll keep it this pH. We need to figure out what buffer we want to use. We go look at a chart, we figure out what acid has a pKa close to the pH that we want. So here's what I was just saying. Pick a weak acid whose pKa is close to the desired pH. And then if you want to figure out exactly what concentrations you need to get exactly that pH you want, you just plug in. So just plug in to figure out what this ratio is. And then we just do like a 1 to whatever ratio. So here's an example. So you could probably pick here pH of 9.5. Here's the pKa. Probably pick either one of these. I think that HCN is closest, so I'd probably pick that one. So if we pick HCN, so how would we? So let's pick our HCN because it's got the closest to 9.5. You probably could also pick this guy, but the HCN is closest. So pH, we want 9.5, pKa 9.21, plus log of, I need to know what's that ratio, and just solve for x. And you're like, oh yeah, just solve for x. You remember how we get out of logs? You have to raise it to the power of 10. Like I said, I don't have a calculator with me, so it looks like they don't do it in steps. Let me pull up my computer. I can't do subtraction to save my life. Not quite obviously. Should be able to do this in my head. So we got 0.29 equals log of x. Raise everybody to the power of 10. And that'll be your x. And remember, x is your ratio. X is equal to the ratio of the A minus over HA. So we get an x of 0.32. So what do we do with that? So now that we know the ratio is 0.32, we could say 0.32. Oh, that's not right. They used a different one, so I can't say that one. 10 to the negative, using negative, wait, why did I do negative? 10 to the positive 0.29. I'm just so used to doing the pH. I get 1.94, 1.95 probably if I round, equals the ratio between A minus to HA. So let's think about what that ratio means. For every 1 mole of HA, I would have 1.95. So this could be like 1.1. Just put it over 1. 1.95 mole of A minus. So we would need to take, we could even change that to molarity now. We could take a 1 molar HCN solution and 1.95 molar CN minus, maybe like sodium cyanide, and that would make our buffer solution. So we could say like 50 mils of that and 50 mils of this, like same amount to get the same moles. And there you go. Now we made a buffer, and the buffer will keep the pH around 9.5. All right, that's it for this video. We'll come back for the next one.